Hey Chem 240, Dr. Ricardo. This is the last section of chapter 17. Should just be about 10 minutes. Starting in the notes on page 29, we're going to talk about one last form of equilibrium. So far, just to review, we've talked about Kc, which is a regular equilibrium constant, Kp, which is the equilibrium constant in terms of pressure. That was in chapter 15. In chapter 16 and 17, we talked about Kas, which was the equilibrium constant for weak acids, Kbs, the equilibrium constant for weak bases, Kw, which is the equilibrium constant for water, right? The autoionization of water. And in the last chapter, in the beginning of chapter 17, we talked about Ksp, which is the equilibrium constant for insoluble salts dissolving to just or slightly soluble salts dissolving to a small degree in water, leaving mostly precipitate, but just a little bit of it dissolving. So those are Ksp. So here's the last kind. The last kind are going to be Kfs. So they are the formation constant of complex ions. So I'll explain to you what complex ions are in a second. But formation means to make the complex ion out of its subsequent parts. Usually there's a metal center, some kind of positively charged ion in solution. These are all going to be solution reactions, and we're only going to deal with them in concentration. And then you're going to have a certain amount of usually negatively charged species called ligands, which can be either have a net charge on them or just be neutral like ammonia, but have electrons that they can donate into the metal. See, the metal is positive charge. It's looking to have these ions stuck to it. So here's a case where we have a metal plus 2, 6 ligands. These ligands are also dissolved, right? Nothing is precipitated at the bottom, and it makes this neat complex Ml6 plus 2, where the metal, we call it the metal center, and this is hexa-coordinated, which means it has 6 ligands around it. Okay, the crystal structure or the formation of it, which you would have learned from Chem 1, is this is called an octahedral coordination, right? Because there's one on the top, one on the bottom, one to the left, one to the right, one in the front, and one in the back. Or the way I have it drawn here is 2 of them are sort of sticking out on an angle in the front, and these 2 guys here are back behind the blackboard. You think of the metal being straight in the blackboard. This guy's on top, this guy's on bottom. These 2 guys are sticking out, one to the left and one to the right. This guy would be in the back right, this guy would be in the back left. Okay? So again, 4 around a square and 1 up, 1 down. Okay? All right, so how would you describe the Kfs? The Kfs, just like all Ks, you take the concentration of the product divided by the concentration of the reactants. Coefficients become the exponents, so this guy is just to the first power here. This guy here is to the 6th power, and this guy is to the first power. So these Kf values, right, usually are going to be enormously large numbers because these concentrations, something to the 6th power in the denominator, is going to make this number very, very, very large. So opposite of KSPs, the formation constants for these metal ligand complexes are going to be very large numbers. Okay, so let's read through this first, and then we'll just look at one example. Now, neat thing is, a lot of you guys are going into biology. A lot of these complexes are sort of biological molecules as well, and these complexes are going to be important to a lot of different processes in biochemistry. One of the classic ones is you think about hemoglobin. The heme units are ligands. There are 4 of them that surround the metal ion. So you can talk about the complex of iron with heme, or to make heme, and so the iron plus the individual ligands to get together. Okay, so let's read through this definition. So complex ions are formed from a metal ion with Lewis bases, right, which are electron pair donors, attached to it by coordinate covalent bonds. So both of the electrons are coming from the ligand, and they're pushing into the metal ion, which is positively charged. So that's called a coordinate covalent bond, when both electrons come from the same place. Okay, so the ligands, in this case, they're neutral, right? So this would be a metal ion with, could be 6 ammonias around it, okay? So here goes one pushing in, here goes another one, here goes another one, here goes another one, here goes another one, here goes another. The whole complex has no charge. The ligands can also be ions, negatively charged ions, and you just have to account for the total charge. Let's say each one of these was a -1 and the metal was a +2. So you'd have a -6 from the 6 ligands and a +2. The whole thing would be -4. So that's pretty easy to take care of. And I'll show you some examples. So these are really neat things. Okay. So a classic example of 6 ammonias pushing in on a copper would make a beautiful blue ammonium solution, copper ammonium solution. Okay, you can do this with iron. A lot of these metals form important complexes in biology. Okay, flip it around. You can look at this as the dissociation constant, Kd, for the complex ion is just the opposite reaction. Take the same exact metal ion complex and think about it breaking apart to give back the metal with no ligands around it, plus the 6 ligands. Kd then is going to be this times this to the 6th divided by the complex in the denominator. So it's pretty easy to see that the dissociation constant, Kd, for a complex ion is just 1 over the formation constant. Here's formation, right? Here's the formation reaction. Here's, put that up there. Here's dissociation. Look at those two things. Formation, see if I can get them both on there. How's that? Look at the top one. The top one and the bottom one, go up a little bit more. How's that? Top one and the bottom one are just flipped over. This one has the complex ion in the numerator. This one has it in the denominator. These two things here are in the numerator. Here they're in the denominator. So relationship between Kd, the dissociation constant for a complex ion, and Kf, the formation complex, very simple. They're just reciprocal to one another. They're not related to Kw or anything like that. Remember, Ka and Kb are not just reciprocal to one another. Ka is not equal to 1 over Kb. They're related through Kw. Ka is equal to Kw divided by Kb. Or Kb is equal to Kw divided by Ka. So that's different. Good. All right, last thing. Just going to show you one graph on the textbook. So this is textbook page 748. It just gives you a bunch of different examples of coordination compounds from metal ions in solution. So again, really important in biology because a lot of times we need metals in our body, but we can't just ingest them in the form of a chloride. We need to sneak them into our bodies. So the best way to sneak them is through these complex ions. So a lot of vitamins are designed this way. If you needed to get, for instance, if somebody needed to get, well, cyanide you wouldn't do, but if you needed to get, so let's say someone had a cobalt deficiency, right? Then they could take it this way. Here's ammonia, here's copper with ammonia, which is one of the ones that we talked about. So all of these things, look at them. All the complex ions, these are all dissolved ions. They happen to, let me see, I can blow it up a little bit more. Let me see if they're all charged. They don't have to be. Well, actually they are. I don't see any neutral ones. So they all have a net charge. So for instance, take a look at this one here. Zinc, instead of precipitating with hydroxide, it actually gets 4 hydroxide ions around it. The zinc was +2. Each hydroxide is -1. So the 4 hydroxides equal -4. And they put it together with the zinc that's +2. The overall charge of the complex is -2. Well, look at this number, 6.4 times 10 to the minus 17th, 10 to the positive 17th, and it represents this reaction. Zinc plus 2 getting together with 4 hydroxides to make zinc hydroxide in solution. Okay, this one would not be colored, but pretty neat way. So you can sort of solubilize the zinc in very basic solution. Okay, so instead of forming a precipitate, it does the other thing. It forms these complexes. Let's take a look at one other one. Here's a neat one, right? Aluminum actually forms with 3 hydroxides. It forms a precipitate. But if you push past that and go to very high pHs, you can actually get it to redissolve. And you get it to redissolve not by the 3 OHs coming off. You can get it to redissolve by putting one more on. So let me just show you that really quickly. That's kind of neat. Okay, so I'm telling you, aluminum is not very soluble with hydroxide. This is an insoluble salt. So if I put an extra OH on, I take this insoluble salt and I can solubilize it in very basic solutions, right? Push it to the limit and I can make this thing, which is soluble, put 4 of them on there, make it a -1. So I can make this out of something that's insoluble. Okay, so starting from scratch, making it from the individual ions, here's what it looks like. That guy right there. Okay, so it has a K formation of 1.1 times 10 to the 33rd. I can play around with the KSP for this and this guy over here, and I could come up with this equation. That would be a fun one to do. Okay, you can come up with this by taking the KSP of this and putting it together with the formation constant given here. Okay, and you can see what you get. What would be the K for this reaction happening? Okay, and now this guy has a cool K, right? This guy's K is just one guy in the numerator. This guy's Kc is this guy in the numerator and this guy in the denominator, right? Because this is a solid, so I would leave it out. So try that out yourself. See if you can get Kc for this from the KSP for this. Look up the KSP for this and the KF here. Okay, take a little break, do that. That would be kind of fun homework assignment for you. Okay, you should be able to do it. All right, so that's it for chapter 17. Thanks, guys.